Okay, so welcome to you all for this new course on fundamentals of solar photovoltaics and technologies. This is the first lecture of this course. My name is Ashish Garg. I am professor at the Department of Sustainable Energy Engineering of IIT Kanpur. My email ID, which is written on the screen, is ashishg@iitk.ac.in, and you can also look at my website for any other information related to me. So this course, in the following slides, I will tell you briefly about what we are going to do in the course, followed by the start of the course. So the first of all, who all can take this course? This course is suitable for any undergraduate student who is in third or fourth year, or a postgraduate early career student, typically from branches like material science and engineering, metallurgical engineering, electrical engineering, mechanical engineering, chemical engineering, energy engineering, physics as well as chemistry. However, it is not restricted only to these branches. If any other student is interested in this course with due preparation in background information related to material science and solid state physics, any other branches are also applicable. So let us first look at the objectives of the course, what the objectives of the course are. This course expects to provide insight to all of you in different aspects of solar photovoltaic technologies. We will cover aspects such as solar radiation, basic physics of materials that are used for PV applications. Since most of the solar cells that we employ in commercial applications work on PN junction based device architecture, this course will provide insights into PN junctions and their operations under light as well as dark, and it will also provide information and insights into photovoltaic devices of different generations. They are typically characterized into first, second and third generations. And very importantly, the course will also provide learnings about materials that we use in not only state of the art devices, but also in other devices, including their manufacturing and characterization methods. So basically, it is an introductory course for advanced UG and PG students, early career PG you can say, students who wish to learn about solar photovoltaics for the first time, who wish to enhance their knowledge about materials and devices related to solar photovoltaics. So what do you expect to learn from this course? Well, you will be able to understand first of all the photovoltaic devices and their fundamentals, how they work. You will be able to understand the physics of variety of processes, including device processes, materials processes, the processes, optoelectronic processes related to carrier generation, carrier movement, carrier recombination, etc. You will also be able to learn about PN junction operations in both dark and light, and you will be able to learn characterization methods for solar cells and how are they made, what different technologies are, and what are the state of the art at the moment. And with hope that you will be able to apply these knowledges and fundamentals into practice at work if you are working in industry, or in research if you want to pursue your career in research. So the course contents, well, it should be 60 lectures of 30 minutes each. It is approximately 30 minutes each. So in that sense, it is a 12-week course, each week having 5 lectures of 30 minutes each, and the course will start from solar radiations. We will look at the fundamentals of solar radiation, how is it measured, what are the fundamentals of solar geometry and angular relationships, which are very important to maximize the solar, whose understanding is very important to maximize the amount of solar radiation that you get on a given location at a given time, and how do you measure the solar radiation. Second part is about learning about elementary material science, because all of the solar cells rely on certain class of materials. So understand materials, we will just look at some very basic fundamentals like what materials crystal structures are, what are planes and directions. Knowledge of planes and directions is important if you choose a single crystal or polycrystal. What is the difference between a single crystal and a polycrystal, for example, what the defects are, and what are the different forms of materials that are utilized in photovoltaic devices. In the week 3, we will learn about very basics of semiconductors, because most of the materials that we use for photovoltaic applications, they happen to be semiconductors. So we will learn about things like energy bands and material classes, very basics of semiconducting materials, what is the difference between an intrinsic and extrinsic semiconductor, what do we mean by carrier concentrations in these contexts, and what is the conductivity, electrical conductivity and electrical mobility or electronic mobility of semiconductors, which is a very important parameter for any optical devices, but particularly photovoltaic applications. In the week 4, we will look at electrical and optical processes and semiconductors. Electrical and optical processes are the processes that happen inside these semiconductors when you apply an electric field, or when there is a concentration gradient, or when there is an optical stress, for example light. So, there are phenomena such as drift, diffusion, generation, recombination. These 4 play a very important role in determining the final output of a semiconducting device such as photovoltaic cell. We will also learn about continuity equation, which combines all these 4 effects into one equation, and then it can help you understand the changes in carrier concentrations as a function of time or position in the devices. In the week 5, we will look at the very fundamental device structure which is used for semiconductors, such as p-n junctions, where p-type or n-type semiconductor are put together. But not only p-n junctions, we also will learn a little bit about metal semiconductor junctions, because every photovoltaic device, not only it has a semiconductor, but it also has a metal which is in contact with semiconductor, making a junction between the two, and whose characteristics are extremely important to understand the properties or device output. In the week 6, we will learn about p-n junctions in light, and then about solar cells, how does it make a solar cell, and what are the important device parameters of a solar photovoltaic device. In the week 7, we will learn about essential characteristics of solar photovoltaic devices. We will also learn about device characterization, how they are characterized, and we hope to provide you a training on some very basic elementary software to analyze these device properties. In the week 8, we will learn about solar cell manufacturing. This will begin with overview of thin film growth, especially using chemical vapor deposition and physical vapor deposition processes, which are abbreviated as CVD and PVD. And then we will look at device processing, because there is certain device processing that is also involved in case of photovoltaic cells, especially the lithographic processes, and then materials fabrication techniques, especially in the bulk form as well as in the thin film form. So, we will look at bulk semiconductor manufacturing pertaining to silicon, that is silicon manufacturing, looking at metallurgical grade silicon and how silicon is refined further to convert it into a single crystal silicon, which will be taught in week 9. So, in week 9, we will talk about semiconductor silicon, single crystal silicon, and we will move on to our first generation solar cells, which are based on silicon, and how they are made. And week 10, we will stress upon, we will learn about silicon photovoltaics, which is the bedrock of solar photovoltaics. We will learn about the device structures, the materials that are used in making this photovoltaic device, and also about the manufacturing of these solar cells. Week 11, we will learn about second generation solar cells, primarily focusing on cadmium telluride and copper indium gallium selenide solar cells, which are thin film solar cells. The first generation solar cell happened to be wafer based technology on wafers of thickness 200 to 300 micron thick, but in case of week 11, thin film solar cells are based on thin films which are a few microns thick. So, that is a very new, that is a very interesting technology in itself. And finally, in week 12, we will learn about the third generation solar cells, the contemporary solar cells such as organic solar cells and perovskite solar cells, where a lot of research is going on, and the tandem cells. And also we will look at some applications of photovoltaics, such as building integrated photovoltaics. We will also look at how do you determine a system size, given that you have a certain power requirement, and what are different pitfalls and falls of having that requirement, and also the future outlook of solar photovoltaics. So, this is in a nutshell an introduction, a summary of all the 12 weeks that we will go through. Mind you, the boundaries between the weeks are not very sharp. Sometimes, depending upon the amount of time that we spend upon a topic, there could be a little bit overlap between the weeks. So, please excuse me for that, but more or less we will try to follow this pattern. Coming to books and reading material, the two primary textbooks that we will follow in this course, and which I strongly recommend you to read, are Physics of Solar Cells by Jenny Nelson, which is an Imperial College Press book. It's an excellent book on physics of solar cells as well as technologies. And then second book I will recommend you strongly is Handbook of Photovoltaic Science and Engineering by edited by Luke and Hegedus and published by Wiley. The other books that you can refer to are Thin Film Solar Cells by K.L. Chopra, which is published by McGraw-Hill, Physics of Solar Cells from Basic Principles to Advanced Concepts by Peter Werfel, which is published by Wiley, and then third could be Photovoltaic Materials by Richard Bube, which is again published by Imperial College Press. However, books do not necessarily cover all the technologies, especially third generation technologies. So, for those new topics, we will refer to various reviews and journal articles, and whose online link or the address I will provide you in the slides, and you can go and read them yourself. I would strongly recommend you to go through the books, as lectures on this video may only be partially sufficient if you really want to become expert in the area. There will be two teaching assistants for the course. First is Mr. Shailesh Kumar Sah, who is a PhD student at the Department of Sustainable Energy Engineering at IIT Kanpur, and whose email ID and mobile numbers are written here. And second one is Pramod Yadav. He is again a PhD student at the Department of Sustainable Energy Engineering at IIT Kanpur, and again whose email ID and phone number is also written here. They will be useful in the course when you interact with them during your assignments and other queries. Coming to the prerequisites, what you must know before you start this course. First is you should have reasonably good knowledge of solid state physics or quantum mechanics or physics of materials, as we call them. And secondly, you should also know some basic elementary material science. So, I have written down a few books that you can refer to build your background or to strengthen your background. Material science related books, you can consider reading Material Science and Engineering, a first course by Professor V. Raghavan, who was a professor at IIT Delhi long time ago. This is a easily available, very low cost book and an excellent book. And second book that is also available in India at a reasonably low cost, I believe, is Material Science and Engineering, an Introduction by W.D. Callister. This is again a very, very popular book on material science. This will help you these two books, either of these two books will help you understand the basic elementary material science which is required to understand this course in the context of materials and their forms. Second important book on quantum mechanics, or you can say solid state physics. So, I can also write solid is first one is Solid State Physics by Charles Kittel, which is published by Wiley. It is a very, very popular book. Second book is Electronic Properties of Materials by R.E. Hummel, which is published by Springer. If you want to learn specifically about semiconductors fundamentals, I would strongly recommend Robert Pierre's book on Semiconductor Fundamentals Volume 1 and Volume 6, Advanced Semiconductor Fundamentals, which is published by Pearson. And if you wanted to learn more about devices, the first book is Physics of Semiconductor Devices by SMZ, published by Wiley, and second is Solid State Electronic Devices, written by Ben Streetman, published by Prentice Hall of India. So, these are the books that you can refer to build your background knowledge. As far as functioning of the course is concerned, you will be provided assignment on a weekly basis, and these assignments will consist of different types of problems, objective types as well as calculation type, and exams will also be conducted online, and exams will carry questions which are of objective type or numericals. Okay, so the first thing is, why should we study this course? What is the motivation for studying this course? The motivation for studying this course lies in the energy demand that has been soaring worldwide. As we grow to become a large and large country, we are already 1.4 billion, the world population is already 8 billion, and as we become even bigger in size, our energy demand will grow. And most of this energy demand is based on use of fossil fuels, which are natural resources for us, such as oil, gas and coal, and they cause environmental pollution. And to prevent that pollution, it is important for us to switch to renewable sources of energy such as solar energy, which is abundant in nature, and it also brings a lot of social benefits to the society. So we will go through these aspects in next few slides and see what is really the need of using renewable energy such as solar photovoltaics for energy generation. Historically, if you look at, there have been several sources of energy. The first and foremost source of energy for humans were food and fire. Fire allowed people to burn forests to create dwellings. Fire allowed humans to cook the meat to eat, and fire also provided them heat, which was needed during cold times. Then, as the civilization grew, we became from forest dweller to a man, a woman who started using metals. So if you look at our civilizations such as Bronze Age or Iron Age, they were built around using metals. Metals are not available in nature in their raw form. Metals have to be manufactured from ores or oxides. And this is where metallurgy evolved, and metallurgy used high temperatures, and this high temperature required some source of energy, typically biomass or wood, some sort of fossil fuel based method, which provided high temperature for us to, enabling us to reduce these oxides into liquid metal, which was then solidified into solid metals. And metals really paved the way for our civilization. They helped us do a lot of good things as well as bad things such as wars. But anyway, it was a very important technological turning point, but it required a huge amount of energy. And this energy came from biomass or natural sources. And in more, after the Industrial Revolution and after the invention of coal, we stumbled upon something called as electricity. And today, without electricity, we cannot live. I mean, this lecture which is being broadcasted is mainly because we are using the fundamentals of electricity, and of course, we are using optical fiber cables, etc. But electricity plays a very important role in our lives today. And this electricity, by and large, until recently, has been based on use of fossil fuels, namely coal. In the picture, you see the power plant, which is typically run using technologies that burn coal. So basically, coal is burned to produce hot water or steam, and steam is then used to run turbines. Turbines are the entities that provide us electricity. So among all these, in all this story right from prehistoric times to now, energy has played a very, very important role in our development, and we require energy for almost everything that we carry out. We require energy for eat, we require food to work out, to be able to move around, to be able to do variety of activities. That is in the just a bodily context, but we require nowadays energy for almost everything that we do, because we use so many gadgets, including our clothes, our devices, all of which need to be manufactured, and their manufacturing requires huge amount of energy. So energy, the quest for energy has driven human beings right from the beginning, whether it was for cooking and heat, or agriculture, as you can see in the picture, or for transport, moving us from one place to another, whether using the man carts or human carts, or by animal carts or cycles, whatever, or modern form of vehicles such as cars or jeeps or trains or aeroplanes. Everything required energy. Wars required energy, because wars required people, animals, and swords and spears. All of this required supply of energy from some source. And now in the modern era, it is the industry, it's goods that we produce, and the huge human consumption that takes place because of these goods and because of our reliance on these goods. All of this requires immense amount of energy. So in the modern times, since the Industrial Revolution, what has played a very important role in increasing the demand of energy as well as supply of energy is the coal mining. And coal mining, earlier it was done manually. It was very, very difficult job for human beings. Many people used to die earlier in coal mines. Invention of steam engine, which was made by James Watt, paved the way for efficient mining or faster mining. and this led to rapidification or fast track mining, and more and more coal was produced, more and coal was used to run industries, and this also paved the way for electricity generation using thermal power plants, and electricity fueled the mechanization and electrification of our industries, and this really was the very important turning point as far as energy usage is concerned. And so this all started with, in the modern context, with coal mining and coal derived energy. So this basically is the foundation of industrialization that happened around 1700-1800 times. So if you look at the Industrial Revolution in 1784, around 1780s, the first industrial revolution occurred, which was about mechanization of steam power. So basically the steam power that we generated, that ran the machines. Later in 1870s, second industrial revolution happened when we started electrifying our processes, and we were able to do assembly line mass production. So in the first stage, we were using coal power to run mills without electricity. Okay, so it was mechanization of steam power to run machines. In the second stage, when electricity was being produced at commercial or large scales, we were able to electrify our assembly lines, and we were able to mass produce at a larger scale. In 1960s, the third industrial revolution occurred, which was about birth of automation and electronics, especially after the birth of semiconductors. And this gave rise to automation of industry, giving rise to even more faster, higher productivity. And the fourth stage happened in around 2010 with the birth of, after the birth of internet and the cyber physical system networks paved the way for digitalization, and this is where fourth industrial revolution happened. And fifth stage, as we all are contemplating, will be artificial intelligence, or it is already underway. Moving from 1700s to 2000s has been continuous increase in energy demand, starting from mechanization to electrification to automation to digitalization, now to artificial intelligence. And this whole energy demand is built upon the exploitation of natural resources, namely fossil fuels. So the conventional sources of energy that we use are basically fossil fuels built upon coal, gas and petroleum. And as we will see, as we should know that India, in the context of our country, we have good coal reserves, but we do not have very strong oil and gas reserves. And this is something that we need to import. As a result, it becomes an expensive operation. It also becomes an operation wherein we are dependent upon others. So right now you can see that between India and Russia, India and US, there is a trade war, and this is built about and United States is trying to impose tariffs on India because of India buying oil from Russia, which is cheaper oil as compared to other sources. Nevertheless, the conventional sources of energy are fossil fuel based on coal, oil and gas. So if you look at this evolution of global primary energy consumption by source from 1800 to 2020, as extracted from this report, BP Statistical Review of World Energy via our World of Data, utilizing the data given by Professor Václav Smil in 2017, we can see in 1800s, when our population, when we were very small, before the Industrial Revolution, or round about the first industrial revolution, we were primarily using traditional biomass for meeting our needs, mainly for heat and muscles for kinetic energy before 1800. After 1800, we started, as the coal mining took place, more and more operations were becoming dependent on coal. We started using coal more and more, and slowly coal starts increasing in its consumption. In about 1859, the first oil well was drilled in US. In 1930, coal usage increased because of growth of steam power and coal-fired power plants. You can see that there is a rapid increase in the coal as it is happening from here to here. And then from 1900 onwards, you can see there is also a rapid increase in oil, and somewhere also we discovered gas, and this gas consumption also started increasing. So you can see that the consumption of coal, traditional biomass remained nearly constant, but consumption of coal, oil and gas kept on increasing with time. In this period, we have also discovered things like nuclear energy and renewable energy. Renewable energy is based on sources of energy that are renewable in nature, non-fossil fuel based, but by and large our energy consumption is built around coal, oil and gas, and this is very much in sync with the human population. So, we can see that in 1800 we were 1 billion people, in 1900 we became 1.6 billion, 1950 we became 2.5 billion, 2000 we were 6.1 billion, and today we are 8.1 billion. And this growth in human population is pretty much in sync. It is roughly of similar nature as the energy growth of the world, which is primarily based around consumption of energy which is produced using sources such as coal, oil and gas. And this is driven by basically you can say technological advancements, variety of industrial activities to produce goods for us and consumption of those goods by us. So, if you look at primary energy consumption worldwide, there are major energy consumers such as United States and China, but there are other consumers which consume energy in the excess of 20,000 terawatts hour, but there are countries such as India which also consumes significant amount of energy, Russia and many other countries. So, this color coded map gives you the energy map of the world, who consumes what amount of energy, and total energy consumption in today's context is about more than 180,000 terawatt hours, which has increased from less than 10,000 terawatt hours in 1800. So, significant increase in the energy consumption which is built around the use of fossil fuels. So, India uses about 10,000 terawatt hours, China uses about 47,000 terawatt hours, America or United States of America uses about 26,000 terawatt hours of energy, and all of this is built around fossil fuel uses. So, you can see concurrently from 1965 to 2023, the production of oil, production of coal and production of gas has steadily increased, and all of these three sources provide us energy ranging from 40,000 terawatt hour to more than 50,000 terawatt hour. So, we can see so far that all of this energy consumption that we do to meet our energy demands is built around the use of fossil fuels, which are primarily oil, coal and gas, and this is still increasing as we go further. So, in the next class what we will do is that we will look at what is the impact of this fossil fuel based energy on the climate change, what kind of negative effects it has on our climate, on our ecosystem and our living, and how we can switch towards renewable energy such as solar energy to meet our future energy demand in the second class. So, this we will discuss in the second lecture. Thank you very much.